In the last lecture, we found that we can interpret a spanning set of a subspace. We could interpret this as a sampling set for the subspace is W. We can interpret a spanning set as a sampling set for W. Viewed from this point of view, we would like to have an optimal sampling set. This means we must remove redundancy from sampling, and this meant we should remove linear dependence and look for a linearly independent spanning set. This led us to the notion of a basis for a subspace as a maximal linearly independent set in W. We also look at it as a linearly independent spanning set, both were equivalent. A basis is either a maximal linearly independent set or it could be interpreted as a linearly independent set which spans the space. Now, from the point of view of sampling, the ideal situation or the simplest situation is when W has a finite basis. So, that our sampling set is a finite sampling set. So, this led us to the notion of a finite dimensional space. Let us recall the definition. Suppose V is a vector space over a field F and W is a subspace of V, and then we say W is a finite dimensional subspace of V if W has a finite basis, if W has a finite basis. In particular, if we take W as V itself, we say V is a finite dimensional vector space, a finite dimensional vector space which from now on in short form we will write it as FDVS, finite dimensional vector space if V has a finite basis. We shall now look at some properties of finite dimensional spaces. Suppose again we start V a vector space over F and W contained in V is a subspace of V and W is finite dimensional. So, we look at a subspace which is finite dimensional and we look at some of the properties of such a subspace. Now, what do we mean by saying that W is a finite dimensional subspace? By definition, this means W must have a finite basis. So, this implies W has a finite basis. So, let us look at a finite basis, say that is a finite basis. So, it must have a finite number of vectors. So, let us say it has d vectors u1, u2 and so on ud. So, suppose W has a finite basis which consists of d vectors. We know it as a finite basis because we know it is a finite dimensional subspace. So, it must have a finite basis. Suppose we have a finite basis and it has d vectors in it, we call them u1, u2, ud. Now, consider any subset in B in W which has d plus 1 vectors. Let us call it as B1 to be V1, V2 and so on Vd, Vd plus 1. So, we have a subspace which is finite dimensional and we have a basis which consists of d vectors. Now, we consider another set which has d plus 1 vectors, one more than the size of the basis. We claim B1 must necessarily be linearly dependent. B1 must necessarily be linearly dependent. What is the reason? Suppose not. Suppose B1 is not linearly dependent. What does that mean? Suppose B1 is linearly independent. Suppose B1 is linearly independent, we will arrive at a contradiction and thereby showing that B1 must be linearly dependent. Suppose B1 is linearly independent. Now, look at V1. V1 belongs to W and we had B is a basis for W, which means it has two properties. One, it must be linearly independent and two, it must span W. So, we use the spanning part of it and hence the space spanned by B must be equal to W. So, we have V1 is in W, but W is spanned by B. So, V1 is in W, W is spanned by B. So, therefore, V1 being in W must be in LB. So, that says V1 is in LB. What is meant by V1 is in LB? That means V1 can be obtained as a linear combination of the B vectors alpha 2 u2 plus alpha d ud. The fact that V1 is in LB means V1 is equal to alpha 1 u1 plus alpha 2 u2 plus alpha d ud. This implies that 1 times V1 plus minus alpha 1 u1 plus etcetera plus minus alpha d ud is the 0 vector. And therefore, we have here a linear combination of the V1 vector and the u1, u2, ud vectors giving rise to the 0 vector. At the same time, at least one of the components, one of the coefficients in the linear combination is non-zero. Here is a non-zero linear coefficient, namely 1, namely the coefficient of V1. So, that says V1 u1 ud must be linearly dependent. So, we have a linear combination in which not all the coefficients are 0 and hence these vectors must be linearly dependent. We have seen that when we have a finite set of linearly dependent vectors, when we scan them from the left, we will hit a first vector which is a linear combination of the previous vectors. So, what we do is we scan from the left, V1 cannot be a linear combination of the previous fellows, Therefore, there is a vector between u1 and ud. As we move, first we hit a vector which is a linear combination of the previous fellows. So, there exists a ui which is a linear combination of v1, u1, u2, ui minus 1. It is a linear combination of all the previous fellows. So, we knock that vector off. So, remove this vector. What do we get? b1, u1, ui minus 1, ui plus 1, etc. ud. Now, this set may or may not be linearly independent. Suppose this is further linear dependent, then we can do the scanning again and then we can knock out a vector which is a linear combination of the preceding ones. Now, that cannot be v1, that cannot be u1, that cannot be ui minus 1, because we have seen these are not linear combinations of the previous fellows. Now, it could be ui plus 1 or ui plus 2 and so on. So, we knock off a vector uj which is where j is bigger than I. So, therefore, if this is not linearly independent, we can find uj where j is greater than or equal to I plus 1 such that uj is a linear combination of all preceding ones. When we say preceding ones, we mean preceding ones in this set with the ui already having been knocked out. Then knock out this vector, remove this vector and then continue this process. So, proceeding this way, finally, we would have reached the end of the show because we would have knocked off ui, then something beyond that, then something beyond that. Since there are only a finite number of vectors, this process will end at a certain stage. Therefore, we get after completing this process v1 and there will be certain number of the ui's that would have been removed. So, what is left is a subset, what is left is a subset of b1. We will write it like this, where b1 is a subset of b, which is linearly independent, and therefore, all the unnecessary vectors have been removed, no more to be removed, and whatever could be spanned by v1, u1, u2, ud could also be spanned by b1 and b1 because only redundant vectors were removed, and what v1, u1, u2, ud can span is all of w because u1, u2, ud already spans w. So, therefore, which is linearly independent, this v1, b1 is linearly independent and spans w. Therefore, this v1, this vector v1 and all these remaining unremoved vectors of b1 forms a basis for w. Now, what we do is, what has v1 done? v1 has elbowed out at least one vector of b, because remember in the scanning process we would have at least thrown one vector out of the b vectors. So, v1 has elbowed at least one vector out of b. Now, we push in v2 and look at this. This will be linearly dependent again because v1, b1 is already a basis and v2 is in that space, and therefore, v2 can be written as a linear combination of these fellows. So, this is linearly dependent. So, we can use the same procedure as above. And again we should start knocking out vectors. We can't knock out V2 because it is not a linear combination of the previous one. We can't knock out V1 because it is not a linear combination of V2. The reason is V1, V2, Vd plus 1 were linearly independent. We have assumed that the V vectors are linearly independent. So, V1 cannot be a linear combination of V2. So, again the knocking out of vectors will take place only from among the B vectors. So, by using the same procedure, we now get a subset B2 of B1 which is itself a subset of B such that V2, V1, B2 is a basis for W. Now, B2 would have been obtained from B by knocking out at least one vector in the first step when V1 elbowed in and one vector when V2 elbowed in. So, at least two vectors from B would have been knocked out to get B2. Now, continuing this process, after R steps we would have elbowed in Vr minus 1 V1 and we would have knocked out all the vectors in B. If we have to knock out all the vectors in B, at each step we knock out at least one. So, R can be at most n after at most d. After d steps all the u vectors would have been knocked out. So, we would get after R steps where R is less than or equal to d, V is a basis for W. Since it is a basis for W, it must be a maximal linearly independent set in W, because a basis is a maximal linearly independent set, and therefore, it cannot be a proper subset of any linearly independent set. This is a contradiction because R is less than D and B1 consists of V1, V2, Vd plus 1 and B1 was assumed to be linearly independent because or since this is a subset of the linearly independent set B1. So, let us go over the argument one more time. We have started with a finite dimensional subspace and therefore, this finite dimensional subspace we are assuming must have a finite basis and we are assuming a basis which has d vectors. And then we were wanted to claim that any d plus 1 vectors will form a linearly dependent set. To prove that, we assume the contrary. Suppose it is linearly independent. If it were linearly independent, step by step we elbowed in one vector after the other from the V set into the basis, knocking out at least one vector of B out of it. At the end of R steps, we get Vr minus 1 V1 and we would have knocked out all the vectors of B. Since we knock out at least one vector in each step, at most n d steps are less than or equal to d, at most d, maybe we would have knocked out 2. So, in less than d steps we might have knocked out all the vectors. So, in at most d steps we would have got a basis consisting of at most d of the V vectors, and since it is a basis it has to be maximal linearly independent. It cannot be a proper subset of any linearly independent set, but it is a proper subset of the linearly independent set B1, which gives us a contradiction. Therefore, our starting supposition that B 1 is linearly independent must be false. Hence, B 1 must be linearly dependent. So, what is the conclusion? The conclusion is that if a subspace W has a basis consisting of D vectors, then any set consists in W consisting of D plus 1 vectors must be linearly dependent. So, anything more than D vectors is forced to be linearly dependent. In fact, D plus 1 consequently any set in W having more than D vectors must be linearly dependent, must be linearly dependent. So, if you have one basis which has D vectors, then anything which is in size bigger than this must be linearly dependent. That is the first important property of finite dimensional spaces that we look at. Now, let us look at the next important property. Suppose W has a basis consisting of D vectors. So, W is a finite dimensional space, it has a finite basis, and suppose it has a finite basis having exactly D vectors. So, let us call this basis as B. Suppose B 1 is any other basis for W. Suppose B 1 is any other basis for W, then B 1 must be linearly independent, because any basis must be a linearly independent set. However, since B already has a basis consisting of D vectors, we have seen just now that a moment there is a basis consisting of D vectors, any set consisting of D plus 1 or more vectors must be linearly dependent. Therefore, if B 1 has more than D vectors, it will become linearly dependent, but since B 1 is a basis, B 1 must be linearly independent. Hence, B 1 must have less than or equal to D vectors, since otherwise it will be linearly dependent. And therefore, it says the moment you have one finite basis, all other bases have to be finite, can add at most that many vectors. So, what is the conclusions? The conclusion is, if W has one basis consisting of D vectors, then every basis of W has to be finite and can contain at most D vectors. So, the moment you have one finite basis, all other bases are forced to be finite and nothing can beat the size of the finite basis that you started with. Let us exploit this further. Suppose W is a finite dimensional subspace. Suppose W is a finite dimensional subspace of the vector space V, and B1 is a basis, and we know now the moment if it is finite dimensional subspace, it has one finite basis, and the moment it has one finite basis, all bases are finite. So, the moment I say B1 is a basis, it must have finite number of vectors. Say it has m vectors, having m vectors, and suppose B2 is a basis that can also have only finite number of vectors. Suppose it has n vectors. So, suppose I have two bases for the subspace, one of them has m vectors and the other one has n vectors. Now, let us look at this basis B1. If B1 basis has m vectors, we have just now seen that if you have one basis having m vectors, all other bases can have at most m vectors. So, any other basis can have at most m vectors. Therefore, in particular B2 must have B2 is a basis. So, B2 must have at most m vectors. That means, n must be less than or equal to m. On the other hand, look at B2 as a basis has n vectors, and the moment you have a basis which has n vectors, any other basis must have at most n vectors. Therefore, any other basis has at most n vectors, and if that is so, B1 must have at most n vectors. That means, m must be less than or equal to m. So, therefore, if I have two bases, one consisting of m number of vectors and the other consisting of n number of vectors, then n must be less than or equal to m and also m must be less than or equal to n. Comparing the two, we get hence m equal to n. So, what this says is, the moment you have a finite dimensional space, no matter which two bases you pick, they must have the same number of vectors, which means all bases for a finite dimensional space have the same number of vectors. So, the main conclusion is, if W is a finite dimensional subspace of a vector space V, then any two bases for W will have the same number of vectors. Or we can say all bases for W will have the same number of vectors. So, if W is a finite dimensional space, no matter which, if you pick one basis and see how many are there, 10. you go and look at any other basis, that will also have 10 vectors, any other basis that will also have 10 vectors, and so on. So, there is this number which is an invariant for all bases, and this number leads us to the following definition. Let W be a finite dimensional, we will write FD, subspace of a vector space B. The number of vectors in any basis, we know that it is irrelevant, whichever basis we choose we will get the same number. So, the number of vectors in any basis is called the dimension of the subspace W. This is an algebraic notion of dimension. There are various interpretations of dimensions. At the moment we will restrict only to the linear algebraic, or what is known as the Hamel dimension. This has to be added, that it is called the Hamel dimension of the subspace, but we will call it only as dimension because we will not be talking about any other dimension in this course. So, the number of vectors in a basis is called the dimension. Let us look at in particular, okay, let us make it even more specific. In particular, if V is itself a finite dimensional vector space, then any two bases will have the same number of vectors. The number of vectors in any basis is called the dimension of W, dimension of V. Let us look at some examples. So, to compute the dimension, all you have to do is catch hold of some basis for the vector space and count how many vectors are there in that basis. So, it is irrelevant which basis you capture, as long as you capture a basis, that is enough, because the number you are going to get is going to be the same whichever basis you capture. So, let us look at the first example is F3, which is our standard example, and we know that B E1, E2, E3 is a basis for F3. What is E1, E2, E3? Recall, E1 is this vector, E2 has the second entry as 1, all others as 0, and E3 as the third entry 1, all others as 0. This we have seen is a basis for F3, and now this has 3 vectors in it, and this has 3 vectors in it. Hence, dimension of F3 is 3. Let us look at the subspace W consisting of all those vectors which are of the form alpha, beta, alpha plus beta, where alpha, beta are in F. Okay. This is the collection of all those vectors whose third component or the third entry the sum of the first 2 entries. Now, we know that B consisting of these vectors u1 1 0 1, u2 0 1 1 is a basis for W. and B has 2 vectors in it, and therefore, dimension of W, hence dimension of W is 2. So, F3 is a 3 dimensional F3 is a 3 dimensional vector space. In that vector space is this 2 dimensional subspace sitting. If I take F to be R, R3 will be our usual space in which we live in, which is a 3 dimensional space, and this W will then become the plane z equal to x plus y, which is a 2 dimensional object. The plane geometrically is a 2 dimensional object. So, this is an algebraic way of looking at that fact. And now extending this idea of F3, Fn, if we take the vector space Fn has basis E1, E2 etc. En, where Ej is that which has 0, 0 etc. until you come to the jth component, which is 0, and all the others are 0 for j equal to 1, 2 up to n. This is the basis for Fn, and since this has B has n vectors in it, and therefore, dimension of Fn is n. Let us next look at the example of 2 by 3 matrices over F. We have already seen that Aij 1 less than or equal to I less than or equal to 2, 1 less than or equal to j less than or equal to 3 is a basis for F23. What is Aij? Aij is the 2 by 3 matrix which has all entries except ijth entry as 0 and ijth entry is 1. For example, A 2 2 means except the second row second entry, which must be 1, all other entries must be 0. So, if you look at these Aijs, they form a basis. How many vectors are there? Well, we are going to put a 1 in this place, 1 in this place, 1 in this place, and so on and so forth. 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. There are 6 places where we can keep moving this 1, and therefore, there are 6 vectors in F23. Therefore, dimension 6 vectors in this basis B, and therefore, dimension of F23 is 2 into 3, which is 6. Similarly, dimension of F m n is equal to m times n. The set of all m by n matrices over F have dimension m times n, and in particular the dimension of this set of all square matrices is n square. Let us now look at another example. So, we have seen the vector space of Fn, we have seen the vector space of F2 by 3 and generalize it to Fm by n. Now, we look at the space of all, the vector space of all polynomials over F. Now, this space is not finite dimensional, because if it were suppose let us say that this is, suppose f x is finite dimensional vector space, then there must be a basis, there must be a finite basis. Say u 1, u 2, u n, say n is the dimension and say there are n bases. So, let suppose it is a finite dimensional vector space and dimension is n, then it must have a finite basis consisting of n vectors. And we have seen that the moment you have a basis consisting of n vectors, any n plus 1 vectors there must be linearly dependent, implies any n plus 1 vectors must be linearly dependent in that space. However, this is contradiction, since 1 x, x squared etcetera x to the n are n plus 1 linearly independent vectors. So, we do have n plus 1. So, whatever n you think of, I can get a linearly independent set which is bigger than that. So, therefore, we cannot have a basis consisting of just n vectors, because then we will have a bigger linearly independent. So, therefore, f x, the space of all polynomials, is an infinite dimensional space, is an infinite dimensional vector space. Now, consider W to be the subspace consisting of all polynomials whose degree is less than or equal to 2. Then B consisting of the polynomial 1 x, x squared is a basis for W, because any polynomial of degree 2 is a linear combination of 1 x, x squared. So, 1 x, x squared span the space and they are linearly independent, and therefore, it is a basis for W. And there are 3 vectors in it, B has 3 vectors, and therefore, dimension of this subspace f 2 x is 3. So, we have an infinite dimensional space, namely f x, the infinite dimensional space of polynomials over f, and inside that space is sitting this finite dimensional subspace f 2 x of polynomials of degree less than or equal to 2. In general, if d is any positive integer, you take any positive integer d and then f d x, the collection or the subspace of all polynomials whose degree is less than or equal to d, is a subspace having dimension. See, when we had f 2, we had 1 x x squared as a basis. When we have f 3, 1 x squared x cubed will be a basis. When we have f d, 1 x squared x d will be a basis, d plus 1, since 1 x squared x d is a basis for f d x, and it has d plus 1 vectors, having d plus 1 vectors. So, we have a large number of finite dimensional subspaces sitting in this infinite dimensional space. Now, let us look at another interesting example, which may be, let us take a set S which has a finite number of elements, say Sk. Suppose we have a set S having a finite number of elements, and then look at the vector space of all functions from S mapping onto the real line. So, it is the set of all functions which map S to R. Now, let us look at whether this is a finite dimensional space or an infinite dimensional space. Now, for each j 1 less than or equal to j less than or equal to k, look at the function f j mapping S to R defined as f j t is 0 if t is not equal to S j, 1 if t equal to S j. So, what it means is, here is the set S, here is the real line R, here are the points in the set. Now, what this function f j does is, it takes S 1 to 0, S k to 0, except S j which goes to 1, all others are going to go to 0. Then look at the functions we get like that. First we get f 1 which takes S 1 to 1 and all others to 0, then we get f 2 which takes S 2 to 1 and all others to 0, and so on. So, we get the collection of functions f j, j equal to 1 to k, they are all in S R. We leave it as an exercise to verify that 1 f j, j equal to 1 to k is a linearly independent set. 2, this f j, j equal to 1 to k is a spanning set for W, for spanning set for this space, whatever name you want to give it, this space F S R. Now, what does that mean? It is a linearly independent set, it is a spanning set, and therefore, forms a basis. How many vectors are there? There are precisely k vectors, namely the function f 1, the function f 2, the function f k, and this has k vectors. Vectors here are all function, because this is a vector space of functions. Therefore, the dimension, hence dimension of f S R is equal to k. So, it is exactly the size of the set S. So, if you take a finite set S and look at all the functions mapping S to R, then the dimension of the space is precisely k. Now, we leave it as an exercise as to verify the following. Suppose S is an infinite set. So, I have an infinite set S, inside that there is a finite set. So, S 1 contained in S is a finite set. Now, look at the space of all functions from S to R. This is going to be an infinite dimensional space. This is going to be an infinite dimensional vector space. Now, look at this subspace W which consists of all the functions S to R such that f s is equal to 0 if S does not belong to S1. In other words, only when you take a point in S1, f will have a non-zero value. The moment you go outside S1, f will take the 0 value. So, we will take only those functions which live inside the set S1 and die off outside the set S1. We say technically saying that the support of these functions is contained in S1. Now, inside S1 the value may be 0 or not 0, we are not worried about it. What we are saying is outside S1 it must necessarily be 0. So, we are looking at all those functions which die off outside the set S1. Now, S1 is a finite set. So, let us call it as S1, S2, Sk as before. Then use above example to see if W is a finite dimensional subspace of FSR, and if so, whether dimension of W is K. So, that we have seen a number of examples of dimension. Let us move on and look at some more properties of finite dimensional vector space. We shall first look at the properties. So, suppose V is a vector space of dimension n. Suppose we have a vector space of dimension n, then we have observed that the moment you have a base, any basis must consist of n vectors, and the moment you have a basis consisting of n vectors, any set consisting of n plus 1 vectors must be linearly dependent. So, any set consisting of any set in V consisting of more than n vectors must be linearly dependent. And secondly, suppose B is a set having n vectors u1, u2, un, and suppose B is a linearly independent set. So, B is a set in V, it has n vectors. Suppose this is linearly independent. Can this be a basis? Well, how can it fail to be a basis? How can B fail to be a basis? It can fail to be a basis if it fails to span the whole space, if LB is not equal to V. So, here is V and this is LB. So, LB is not equal to V. If it so, then there is a vector x outside LB. The moment you choose a vector x outside a subspace and a linearly independent set inside that subspace, we will therefore get the set X union B is linearly independent, which means B is not a maximal linearly independent set, because of the fact that it is contained in a bigger linearly independent. But however, we know that anything consisting of n plus 1 vectors must be linearly dependent, but we have a set consisting of B is a set having n plus 1 vectors and linearly independent, which is a contradiction because dimension is n. Therefore, our assumption that LB is not equal to B is false, and hence B must be a basis. Therefore, B is a basis. So, what is the conclusion? Dimension of V equal to n implies any n linearly independent vectors form a basis. In an n dimensional space, any n linearly independent vectors form a basis. We shall see how we sample vectors using a basis in the next lecture.